And then PCRT also has FAA approvals for some inspections. So fundamentally, PCRT is an NDE method that uses a component's resonance frequency spectrum to inspect it for defects, to perform process monitoring and control, and to perform characterization on components. So during our inspection, we are exciting these natural resonance modes of vibration, and then we record that frequency data and use a variety of sophisticated pattern recognition, machine learning, and statistical scoring tools to analyze those resonance spectra and make determinations about the material state of those components. So the raw data looks something like this. Lori, is my cursor visible?
Yes, Eric, it is.
Fantastic. Thanks for the confirmation.
Mhm.
So each line in this each resonance spectrum trace is for an individual part. And every time we see a spike in that amplitude, that is a resonance mode that we've excited, a natural frequency at which that component will tend to vibrate if we input some energy to it. We record all of that frequency information. And the actual physical state of components when we're resonating them look like this, these natural modes of vibration, and we can get different mode shapes at different frequencies. So by exciting these resonance modes, we can detect the presence of defects, understand material state variations in these parts, because the resonance spectrum of a component is dependent on its material state, and it will be affected by the presence of defects, variations in geometry, anything that can affect the structural performance of the parts. Those are things that will affect the resonance frequencies. And this long list of conditions on the right are some of the things that we can detect in AM applications, but by no means is this all inclusive. So there's a lot we can do with resonance in AM. And some of those things include ensuring that we're making the same part every time over time, because resonance is a quantitative measure of a component's material state. We can quantitatively evaluate the consistency of component populations. We can detect material issues that are often invisible to other inspection methods. Resonance is a whole body volumetric inspection method. So the presence of flaws anywhere in the component that will affect structural integrity will affect its resonance spectrum too. And since we're a highly quantitative method, we can do a lot of work to correlate quantitatively to other sources of data, whether that's information on your feedstock material, on your build process parameters, on post-processing information, on other NDT methods, mechanical testing. Those are all things that we can correlate resonance data to and create this sort of data fusion approach where we mash lots of different types of data together, and resonance can be a significant component of that. And since resonance is sort of a fingerprint of components, we can also evaluate the change in material over time. If you have a component that is going through a manufacturing post-process like heat treatment or hot isostatic pressing, or it's monitored throughout its service life, it goes through periodic repair and overhaul, we can scan the resonance frequencies at different points in that part's lifespan and see how the resonance frequencies are changing and give you an idea of how that part is changing in service. So PCRT offers a lot of significant advantages for additive manufacturing. I've already covered some of the defect detection elements of it. So we detect material state conditions that affect structural performance. They correlate to other sources of data like mechanical testing data, AM build process information, and so on. And as I mentioned, it's a wholly volumetric inspection. We're vibrating the entire component during our test. And as an America Makes study found, PCRT is one of only 2 NDE methods, the other being computed tomography, that can cope with the full range of geometric complexity that's possible in additive manufacturing. The method is also highly automated. The entire scan is performed automatically, and the machine learning statistical analysis tools that are applied to that resonance spectrum work automatically and return an automated red light, green light, pass-fail result that doesn't require any operator interpretation. The systems are also highly automatable. We can introduce fully automated part handling to reduce operator touch time and reduce cycle time or increase throughput. And speed is another hallmark of the method. Pass-fail production testing typically requires less than 30 seconds per part. Often it can be accomplished in as little as 5 or 10 seconds. So it's a very, very fast method that allows rapid 100% inspection of full part populations. And then we also offer a lot of capabilities for material characterization. Since the resonance is sort of a quantitative fingerprint of a part, we can use that to derive material properties of that component, elastic properties like Young's modulus and Poisson's ratio, for example, also use it for comparisons to other methods, looking for consistency in populations and so on. And then we also have a lot of capabilities for modeling and simulation tools. So taking a 3D solid model of a part, predicting its resonance frequencies, and then using that for comparison to physical parts. We can also use it to augment reference populations, characterize material properties, and so on. Cost is another significant advantage for the method. It offers significant cost advantages over other NDE methods, particularly some of the more complex, time-consuming ones like CT. CT comes with a lot of equipment costs. It requires a lot of operator training and involvement. PCRT's training requirements are quite minimal, and its equipment is very simple. The equipment is really all about getting a set of piezoelectric transducers in contact with the part to run the resonance scan. Our scan comprises a swept sine wave excitation. So we begin exciting the part through this drive transducer, and we continuously increase the frequency of the excitation. And anytime we hit a natural mode of vibration, we see a spike in the amplitude of our signal, and that's the resonance mode that we record into our database. Swept sine excitation offers a lot of advantages over other forms of resonance excitation. It gives us greater frequency range, control, precision, repeatability of the resonance signal. So swept sine has a lot of power behind it. We can excite a tremendous frequency range. The transducers can go from about 500 hertz all the way up to 12 megahertz, and we have transceivers that can cover that entire range as well. We also perform an automated compensation for variation in part temperature during the test, because change in a part's temperature can affect its resonance frequencies. So we automatically compensate that to ensure that we're getting repeatable, reliable data. DCRT systems come in all shapes and sizes, just like your components. And we configure transducers to hold and excite components in a variety of different ways. And that's usually an optimization between maximizing data quality and maximizing operability and throughput. So we can excite just about any part geometry. I mentioned that America Makes study that covered PCRT capabilities for AM part complexity. So we have systems that also scale with the level of automatability you may want. We have very simple tabletop engineering grade fixtures that are very reconfigurable, all the way up to fully automated part testing systems with automated part handling and repeatable part placement and so on. For the additive manufacturing realm, we've configured a system architecture called the REX for Resonance Expert. And this is an agile system that's optimized for part number flexibility. Doesn't use any fixed tooling. It just has a vision system that guides the transducers into the appropriate contact with the part, and it can accommodate pretty much any part geometry. And this kind of architecture is ideal for additive manufacturing applications where you have a very high mix of different part numbers and different geometries, and you just want one system that can test it all. That's what this is designed to do. So with our systems, we begin by gathering raw resonance frequency data like this. So again, each line here is the resonance spectrum from a different part. Every time we see a spike in that signal, that's a resonance mode that we've excited. So we tag these in our resonance frequency database. So when we look at mode 2 from part to part, that's always the same mode shape in every part. So perhaps that's the first torsional mode. And then number 3, that may be the first breathing extensional mode. And then 4 and 5, those may be the second, third bending modes, for example. So we tag all of these modes of vibration that look like they'd be viable for analysis, and those go into a database that is the fodder for our various analysis engines. And these analysis engines come in a few different flavors. For starters, our initial look at many populations, it's population-based, where we're looking at variation within and between populations, and we're identifying individual components that have a significant resonance frequency difference from the rest of the population, an outlier screening approach. And that process is covered by ASTM standard practice E3081. And then for additional sensitivity to targeted defects of interest, we can take a step up in complexity and apply a process called targeted defect detection, which is described by standard practice E2534. That applies a set of machine learning pattern recognition algorithms that identify resonance mode patterns that are diagnostic for the targeted defects of interest. And then it configures pass or fail statistical criteria for that resonance peak pattern. And we can apply multiple targeted sorts in sort of a chained approach where they run in sequence. And to pass, the part may have to pass all of those inspections. And if it fails any one, it could either be rejected or quarantined for additional examination. We have a lot of flexibility in the way that we can configure these pass-fail inspections. And then finally, we can also look and sort of drill down to be exquisitely sensitive to the formation of flaws in individual components with what we call a part-to-itself approach. So we can take 2 scans or more of a component, an individual part, before and after some step, whether that is a manufacturing process like heat treatment or HIP, or perhaps a service interval for a part that is periodically overhauled. And we can compare the latest resonance scan to its prior resonance scan before that step took place and look at the change in resonance frequencies to indicate the formation of a defect or to monitor and control a manufacturing post-process. So several different ways that we can apply that. And that's covered by ASTM E3213. So all of these approaches have demonstrated reduction in field failures for our customers, improved their operational costs, improved their inspection throughput. So we've had a lot of positive impact on our customers with these methods. So some examples of the application of these different methods. Again, for E3081, this is looking at screening, screening for outliers and quantifying variation within and between populations. So what we do with the outlier screening approach is distill the resonance spectrum information for each part down to 2 statistical metrics. The first is capturing bulk variation in the resonance pattern, and that's indicated by these orange arrows here. You can see that this line, this resonance spectrum, most of these peaks are shifted to the right towards higher frequencies. So that's a bulk material state difference between that component and the other components in the population. And in the statistical scoring realm, that translates to a higher value on the x-axis of this plot, this average resonance frequency, or what we call the z-score average. Conversely, if all these peaks had shifted lower, we'd see a lower value on that metric. And this metric is capturing, again, bulk material changes, so a bulk density difference, a bulk difference in Young's modulus. All of those are things that will drive higher or lower values on this resonance frequency average value. And then the y-axis is capturing the standard deviation or pattern changes in the resonance frequencies. So this blue arrow indicates a point where this resonance mode is pretty much in line with the same mode in the other components in this population, but then the neighboring peak has shifted closer to it. So that's a pattern change where some modes are changing in the part, but others are not. And the more of that we have in a component, the more resonance spectrum pattern change you have, the higher value you're going to have on that z-score average. I'm sorry, that z-score standard deviation, rather. And what that's capturing is localized variations in a component. So a localized flaw or geometry change. The more of those localized variations you have, or the more severe they are, the greater this pattern difference is going to be, and the higher that z-score standard deviation will be. So we plot those 2 values versus each other, and then we see that the normal population here generally clusters into a point cloud. We can apply a boundary around that can be set as a pass or fail limit, and then any part that falls outside of that is an outlier and can be flagged or outright rejected depending on what the inspection process calls for. And here's one example of an application of that for additive manufacturing. These are Ti-6-4 components made with electron beam powder bed fusion, and a small region in each of those components was printed with a different hatch spacing to introduce lack of fusion porosity. And then we scanned the resonance data for all of them and plotted it in a z-score, and we see that that localized LOF region produced a higher value on the z-score standard deviation. There was a marked gap between the nominal population and the off-nominal. So one example of characterizing these populations with this outlier screening approach. The more targeted defect detection mode uses a set of tools called vibrational pattern recognition, or VIPER. And again, that's a set of machine learning pattern recognition tools combined with Mahalanobis Taguchi Systems statistical scoring that identifies diagnostic mode patterns and establishes statistical criteria for them. And what we do is apply usually 2 statistical scores. One is the MTS score, and that captures a part's similarity to a known reference population of good components. So to pass, the part has to be similar enough to the good population. And if it exceeds that MTS score, in this case, falling above the x-axis on this line, it fails, it's rejected. That's sort of the coarse filter. It captures parts that have a significant difference from the nominal population. We can also apply a second filter, a finer filter called the bias discriminator. And that's capturing a part similarity to a known unacceptable reference population. So if that's available for training the machine learning algorithms, we can establish that bias discriminator criterion. And that's captured in this y-axis here. So any part falling to the right of the y-axis is rejected. So anything above the x-axis, it doesn't look like the good parts and it's rejected. Anything that falls too far to the right, it looks too much like the defective population, it's rejected. So parts have to fall in this lower left quadrant here. They're similar to the goods, they're different from the bads, and that's how it gets accepted. So this example in this plot is for a set of auxiliary power unit or APU turbine blades that were subjected to an additive repair process. So additive material was added to the tip, and we demonstrated PCRT's ability to detect porosity in that additively repaired region. In this case, we actually found some parts that had been misclassified by computed tomography, so demonstrated a high level of sensitivity to a fairly small flaws in a fairly small region of those blades. For another example of parts that were wholly built with additive manufacturing, these were some ALSI10MG components, and they were made with a variety of process parameters. We had two nominal populations, so two separate builds. So we captured some build-to-build variation in our nominal set. And then there was a set that was built with low laser power throughout the entire component, so bulk material property change. Another set that was built with low power just in the core region, so a more localized material property change. And then parts that were built with some suboptimal airflow flowing through the build chamber. We demonstrated the ability of PCRT to reject all of those off-nominal conditions with a single set of diagnostic modes. So a single Viper-based sorting module was able to pass all the nominal parts, reject all of the off-nominal parts. And finally, that part to itself approach defined by E3213, in the additive manufacturing realm, most frequently we're applying this to post-processing like heat treatment or HIP. And the example here on the right is looking at those same Ti-64 components I mentioned earlier with the local lack of fusion condition. That full population was subjected to HIP, and the idea was to see if HIP had a healing effect on the defective component or not. And the part to itself data that we captured showed that the off-nominal components had a greater frequency change. So nearly all those parts had frequency changes that fell above the frequency changes for the nominal. And as a whole, the population averages were significantly different. So it demonstrated that the off-nominal parts did change more as a result of HIP than the nominal components did. And if we want to, we can establish statistical process control boundaries on the frequency change for a process. In this case, it's applied to heat treatment operations, where we found in one case for a customer that an area of their furnace was producing much less frequency change than the other areas. So those parts were being insufficiently heat treated. And we enabled the customer to make updates to that area of the furnace to bring it in line with the other areas and improve the consistency of their process. So in a serial production analysis and sorting environment, this is the sort of interface that a user would see. This is a Viper-based sorting module that uses 4 diagnostic modes of vibration to run a pass or fail test. And the scan is first performed in what we call the low-res scan, where it's just identifying the peak, making sure that all the peaks are present in the bands we're looking for. And then that scan is repeated in high resolution to get very high fidelity frequency data for all of those modes. And then the frequency information for those 4 modes is run through the Viper statistical scoring criteria, and it renders a pass or fail result. In the case of this part, it gives a green light pass result. This entire sweep took less than 5 seconds to scan the part and return a pass or fail result. So very, very fast. We also can store all these results permanently, and if parts are serialized, we can store them by serial number. We can also capture information about the batch, what machine the part came from, a lot of other information for traceability. And in addition to the basic pass or fail result, we capture the statistical scoring criteria, whether it's a Viper sort or an Outlier Screening Z-score based sort, and we capture raw frequency information too. So there's a very data-rich set of results that we capture with any inspection. Now, going from basic pass or fail testing and other process control measures to some other things we can do with PCRT, we start with operations with models. Additive manufacturing is fundamentally a model-based process. We almost always begin with a 3D solid model, or in some cases, we begin with a physical part that we want to reverse engineer into something we can make additively, and that usually involves scanning it into a 3D solid model. What we can do with the resonance information, that quantitative fingerprint of the part's material state, is use it to either increase the accuracy of our model or tune our build parameters to better reflect our original model design. So if we begin with a model and we start making physical parts, you can take the resonance spectra from the physical parts and compare it to resonance spectra predicted by the physics-based model and make adjustments to build parameters so that your physical parts more accurately reflect your original design intent. And going the other way, if we're starting with a reverse engineering scenario, we can adjust model parameters based on the resonance spectrum from the physical part to make that model more accurately produce a part that you're trying to reverse engineer. And so with model and measure comparisons, they look like this. We have the means to generate resonance spectrum from physics-based solid models that come from finite element methodology and add them to the PCRT software for direct comparison between the simulated resonance spectrum and the physical resonance spectrum. So this is an example of a comparison that has a good match. The model part and the measured part are very close to each other. In this case, we have a measured part that's a poor match for that original design intent. So that build may need some updates to its build process to more accurately reflect what you were originally intending to build. You can also use PCRT for a lot of different process qualifications. And one fruitful endeavor for us has been the establishment of build maps for additive manufacturing. So for powder bed fusion-based processes, I'm sure many of you know that there can be variation in the material state of components based on where they're located on the build plate. And we can use PCRT to help us quantify those differences. This set of maps on the upper right is for 4 different builds in a powder bed fusion-based process. And the numbers here represent those z-score average values, this x-axis on this z-score plot. We've mapped those values to this and then color coded them in sort of a heat map based approach. And you can see that there are some consistent tendencies from build to build. Like in the upper corner here, we see lower z-score average values for most builds. The lower right, you tend to see lower values as well. So you can use this data to understand how much variability you have from position to position on your build plate. Often the differences between parts in one part of the build plate and another can be greater than the differences between parts made in the same position from different builds. This can also help you make decisions about where you're building different types of parts, make decisions about where you want to put witness coupons, because perhaps a witness coupon that you're going to mechanically test, if you build it over here, it may not be representative of material properties for a part made in the middle. So all of this information can help you make decisions about your builds. You can also use resonance frequency information to characterize the material properties and components. And to do this, we use a process called model inversion, where we start with a modeled population of parts where we introduce material property and geometric variation into that population. And then we measure resonance frequencies from physical parts and do an iterative fit of the measured resonance spectrum to the resonance spectra predicted by that model design space. And the part of that design space that's the best fit for the measured spectrum produces the output material properties that best correspond to the physical part. So on the right-hand side of the window, we show some examples of characterizations for components. This was a aluminum 6061 AM optimized feedstock powder, and it was used to build components. This was the same set of components that I presented targeted defect detection results for a little earlier. So we had our 2 nominal populations. We had our population built with suboptimal airflow, population made with low laser power throughout the part and low laser power throughout the core. We found that a transversely isotropic model was the best fit for this part population. And we see that the nominal components line up quite well with the material properties from the vendor's listed material properties. We see that when we introduce off-nominal processing, we see changes in those material properties like you'd expect. There's more variation within the population, so less consistency for the suboptimal airflow. When the laser power is reduced throughout the part, the average for that population goes down relative to nominal. And then we see a significant level of anisotropy in the low power core. And so that's capturing that discontinuity in material properties between the core region and the external region. Its effective material properties are highly anisotropic. We also captured density information with the model inversion process and found that densities were a bit lower than the original vendor listing values, and that density tends to tail off the farther off nominal we get with our build properties. So this gives you good means to understand what the basic material properties are in your builds, also comparing it to rot populations if you're looking to replace a part made with a legacy process with additive, and just overall understand what sort of material property variations you have in your populations. Next, I'll highlight some examples from a project we perform within the America Makes realm. This is a project that was led by Holly Martin from Youngstown State University. It was looking at effects of defects in powder bed fusion components. And this was part of the Maturation of Advanced Manufacturing for Low-Cost Sustainment, or MAMLS project. The primary objectives of this project were to understand what effect defects like lack of fusion and powder contamination would have on mechanical properties and corrosion behavior in ALSI 10MG. So the program found what sort of build parameters would produce these defective material states, and then measure the relationship between those material states and the ultimate performance of these components. We were focused mainly at looking at the mechanical effects of LOF porosity in our PCRT work. And then a variety of NDE methods and in situ monitoring were applied to this population, including PCRT. These examples I'm going to show came just from the PCRT portion of this project, but if you're interested in the broader scope of this work, I can connect you with Professor Martin and share some additional information with you. There was quite a lot done in this program, and it's an extremely data-rich set of work on effects of defects in AM. So we captured data on a large population of components. There were some bend bars, some E8 coupons, and some E466 coupons. We scanned a frequency range from 3 to 300 kilohertz for these components, again, highlighting the broad set of data you can get with our swept sine approach. And we identified more than 20 resonance modes that were fruitful for analysis of these components. And just looking visually at this spectra stack up, we saw that some builds made with off-nominal components, including groups D, E, and F, showed significant visual resonance frequency differences. They were shifted lower than components from other groups. So just a visual analysis saw that we were already seeing some big differences between some of these components. So we had several different groups in this population. Group A was built with nominal parameters and then was subjected to T6 heat treatment and HIP. Several defective batches were also subjected to T6 heat treatment and HIP, and then some were not. So they were looking for differences between, say, groups E and B, both of which were made with large defects, but E was not subjected to HIP while B was. When we look at the Z-score data for these populations, you can see that there were some significant differences. For example, E had much lower Z-score averages than B, indicating that HIP did have some effect and it helped reduce that gross material property difference. In the Z-score look, Group B actually had frequencies that aligned relatively well with Group A. The resonance indicated that HIP was having a positive effect on those populations. However, you'll see in some of the Viper results in a moment, we were still able to detect differences between the nominal material state and the material state for Group B. Other sets of parts like Group D, which had a large volume of many small to medium defects, although it was subjected to HIP, it still had pretty significantly different frequencies from the rest of the population. So while HIP can be helpful, it by no means is a panacea, and it sometimes can't completely heal defective material states. So I mentioned mechanical testing here. We were very interested in the correlation of resonance frequency information to the mechanical testing results. So we scanned all these components, and then the tensile bars went off for mechanical testing. We established a pass or fail threshold of 306 megapascals for determining whether components had sufficient mechanical performance or not. And then we established a PCRT sort for a set that had been tested in tensile strength. and we trained it to that 306 limit. And then we tested the rest of the population. And overall, we got very good results with this sort. Found that no parts with mechanical performance under 306, so parts that had insufficient tensile strength, all of those, that should say no unacceptable parts passed. that is a misprint. So we rejected all the unacceptable components. Only one acceptable part was misclassified. I mentioned build B, the part that was built with defects and then hipped. Some of those parts responded better to hip than others. We saw that only about half of them had acceptable results. So about half of them passed, slightly more than half were rejected. Similar for build G, which was small to medium defects that had been hipped. Only about half of the, little less than half of them had acceptable mechanical performance. And then the ones that were way off nominal, none of those passed. So PCRT results were well correlated to the tensile testing that was performed on those components. And we saw similar results for fatigue testing. We set a limit of 100 cycles for pass or fail and fatigue. And we found that just about all the nominal parts passed. They had acceptable fatigue performance, and PCRT passed them as well. Build B did better in fatigue than it did in tensile. Majority of those passed, and PCRT reflect that as well, along with build G. And then D, E, and F all had high rates of failure. Lifing analysis was also performed on this population. We did see decreased lifespan for those highly off nominal parts. We did see differences between parts that were built in the X and Z orientations. B, G, and F all had decreased lifespan, despite the fact that B and G had been subjected to HIP. And we found that overall, PCRT was in good agreement with the lifing analysis. So PCRT, along with the other NDE methods that were applied, we did see that demonstrate sensitivity to the defective material states that were built in these components. B and G, those ones that had defects built in but were hipped. In the Z orientation, those tended to have more issues than the ones built in X. Mechanical testing, again, good correlation between PCRT data and the tensile testing results. Again, Z orientation had worse performance in fatigue testing than the X orientation parts. So in summary, both the America Makes work and the other examples I provided, we demonstrated that PCRT offers multiple significant advantages for non-destructive evaluation in AM, and that includes the accuracy of the method, its high speed, low cost, high level of automation. We have strong correlation with mechanical performance, and we've demonstrated these benefits in numerous applications. So my main question is, how can Vibrant and PCRT help you? And with that, I'm happy to take all of your questions.
Eric, thank you so much. Great presentation. Feel free, if you haven't already done so, to put your question in the Q&A box, and Eric will address that. We'll get started with these questions, Eric. Are there any standards or specifications specific to AM that include PCRT?
There are. One of them is one I mentioned early in the presentation, and that was the ASTM E3166. And again, that is a standard guide, so it's informational, highlighting different NDE methods that can be applied to AM components for aerospace applications. There's a section in that guide dedicated to PCRT. As well as that method, as well as that standard, there's also one that's in the ISO balloting process, or should have recently completed it. That's the ISO DTR 52905. That one's being led by Ben Dutton from the Manufacturing Technology Center in the UK. That is also a guide for NDE methods for additive manufacturing. That has a PCRT section. And then there's a standard practice in development through ASTM, the F42 Committee for Additive Manufacturing, that's led by Steve James. And that standard is establishing acceptability criteria for aerospace additive manufacturing components, and it highlights the NDE methods and accompanying standard practices that can be applied to inspect those components, and PCRT is among the methods included in that standard.
Thank you. And Eric, will variation in feedstock powder or machine performance affect PCRT results?
It will, and that's one big advantage of the method is we can detect those effects. Now, it's not a method that's going to characterize feedstock powder before it's actually built into a component. But if there is feedstock powder variation and that drives variation in the ultimate material state of the part, that's something we're going to see in the resonance frequency data. Similarly, machining, the machine was another part of that question.
Yes.
Okay.
Will it affect the machine? Will
Yeah,
machine performance affect results?
Yeah, so we can detect variations in machine performance or machine to machine variation and help users quantify those effects. So if you have a machine that is performing off nominally, we can see that in the resonance data and detect it. So it's a great process control tool for both of those things. And then the process compensated part of process compensated resonance testing is important here too. So we're teaching the inspection to recognize what is normal acceptable variation that we're okay with and detect defective material states in the midst of that normal acceptable variation. So we're maximizing sensitivity to the flaws you don't want while essentially, I guess I don't want to say ignoring, but at least not rejecting parts for those other sources of variation. But we do give you the means to quantify them if you're interested. And that's particularly helpful in process qualification, where perhaps you're standing up a new machine and you want to understand how variable it is from build to build, or understand how consistent it is with your other machines. Or perhaps you're a customer who's purchasing additively manufactured parts from a diverse supply chain of multiple suppliers, and you want to understand how variable these suppliers are relative to each other, or how self-consistent any given supplier is. All the quantitative data that we collect gives you the means to do that.
Okay, I have a few more questions. How large of a population of parts is needed to statistically establish what constitutes a good or bad PCRT scan spectrum?
So ideally, the more components we can get from that, the better. And ideally, we want to capture those normal process variations that I was just talking about. So if we can get parts from multiple builds, we'll understand that build to build variation and we can then compensate for it. Generally, we're looking for some level of statistical significance. So at a bare minimum, we'd want to get at least 30 parts for an initial, outlier screening sort of analysis. But more ideally, if we want to go for like a targeted defect detection approach, we'd want 100 examples of acceptable parts from more than one build. And if we can get them 30 examples of parts with the conditions you're interested in detecting, and that forms a really solid reference set, but we can work with less. It all depends on what you're looking to do with the method. If it is a targeted defect approach, we want to make sure that we have a reference set that allows us to train the algorithms to find that. If you're looking for something that's more of a population variability or outlier screening, we can work with less. And I also want to highlight the power of the modeling and simulation approach. As I mentioned, we can use this to augment reference populations and have at least some of our reference population be simulated resonance spectrum. And that requires us having a model that is calibrated and validated enough to be considered an accurate representation of physical parts. But once we have that, we can simulate those resonance spectrum, and including simulating the effects of defects. And then we incorporate that into the resonance database along with at least some physical parts, because we still need to have this grounded and verified in some physical reality. But we can use that combined physical and simulated reference population to train inspections.
Rick, I have a couple other questions here that you may have just touched on the answer about the process detecting individual defects in a sample, smallest defect size that can be detected. And then again, how many samples to characterize the population for this method?
Okay, I think I've covered the sample size needed. So if there are any additional questions on that, please let me know. As far as sensitivity goes, in a resonance inspection method, the sensitivity is going to be driven by the size of the flaw relative to the size of the component as a whole. That's because we're a volumetric inspection method. So a defect of a given size is going to be easier to find in a smaller component than in a larger component. So there's no one A9095 POD value that I can say applies to all components globally with PCRT. It has to be taken a little bit more on a part-to-part basis. But for components on the scale of, say, aerospace fasteners, so bolts that are a few inches long, we've demonstrated detection of cracks in the threads of those bolts that is competitive with magnetic particle inspection, for example. In other cases, we've demonstrated detection of 50 by 100 micron flaws in very small components. I'm talking like, half-inch diameter or so. So again, there's no one sensitivity value I can say applies to everything, but we have demonstrated high levels of sensitivity to small flaws. Now, as you get into much larger components, so a small crack that you could find with mag particle, if we were to go up to like a 3,000 pound ductile iron casting component, for example, we wouldn't be able to find a small crack in something like that. For a component of that size, we're talking about finding bulk material property differences. But for the scale of most of the components we're working with in additive manufacturing, we've demonstrated detection of small flaws.
Thank you, Eric. I'll give everyone here a moment, if you have additional questions, to type those in the Q&A. I will say this has been a great opportunity for our members that have attended, and for Vibrant, I will remind our members that this is a cost share eligible presentation. Members attending do not accrue cost share, but Vibrant has just accrued $1,500 for this presentation toward the cost of their membership. And this is an amazing way for our members to get the word out of who you are and what it is that you are doing and how we can all work together. And I strongly encourage all of you to take advantage of that. I'm going to put a link in the chat if you're interested in hosting a TRX webinar series. You can click on that America Makes Engage and fill out the form to host, just like Eric did today. And if you want to contact our program manager, Jason Thomas, directly, his email is there. Of course, Eric with Vibrant, his contact information is there as well. So I encourage you to take advantage of the opportunity as a member, and also to reach out to Eric and see how you might be able to collaborate together.
And I think I see one more question that may have popped up in Q&A. Lori, can I answer that one?
Absolutely.
Okay, yeah, so question on the limits of sensing porosity changes in AM materials, considering dimensional variations that are generally greater in AM parts than in machine parts. And yeah, we've absolutely seen that too. In most of the component populations we look at, we do see more geometry variation. That's part of what the process compensated part of DCRT addresses. So with the machine learning tools and our statistical scoring metrics, we're looking at we teach our system to understand what is just normal dimensional variation that's considered acceptable versus the porosity that we may want to detect. In some cases, with a lot of components, there's like variability in component length, just with the plate cutoff, if that plate cutoff is not done with really high precision. So we have some means to compensate for gross variations like that. We can apply some transfer functions to the spectra that help us compensate for that. And then the finer ones are compensated for naturally by the machine learning algorithms. So for cases like those Ti64 coupons with the LOF in that limited region, with the ALSI 10MG coupons that have the different build process parameters, all those are examples of detecting the porosity of interest in the midst of that geometry variation that was inherent in those as-built components.
Well, Eric, thank you once again, and thank you to everyone who has attended today's webinar. Again, contact information is in the chat. Please do reach out to Vibrant or to myself on membership-related questions, or Jason if you're interested in connecting and presenting a TRX webinar. And with that, I will say good afternoon to all of you and thank you once again.
Okay, Lori, thank you very much for hosting this today. Thank you to America Makes for the opportunity, and thanks to everyone here who attended for their attention and questions.
Great. Thank you, Eric.
All right, have a great day, everyone.
Goodbye.
Bye-bye.